A second way of determining the rate order is not to change the concentration of the reactant, say double one, and see the effect on the rate, but simply plot the concentration of the reactants over time and learn what you can from the data. Here's a recording that explains this.
Let's explore the differences between the graphical behavior of different reaction orders. In a zero-order reaction, the concentration decreases in a straight-line fashion as time progresses. The rate constant, K, can be determined from the slope of the line. In a first-order reaction, the concentration does not decrease in a straight-line fashion as time progresses. The graph of concentration versus time is a curve. If the concentration data is graphed as the natural log of the concentration versus time, the result is a straight line. The rate constant, K, can be determined from the slope of the line. In a second-order reaction, the concentration does not decrease in a straight-line fashion as time progresses. The graph of concentration versus time is a curve. For a second-order reaction, the graph of the natural log of concentration versus time will also be a curve. If the concentration data is graphed as the reciprocal of the concentration versus time, the result is a straight line. The rate constant, K, can be determined from the slope of the line.
So let's summarize what they just said. If you're plotting concentration versus time for a given reactant and the plot is linear, well, you're done. It's a zeroth order reaction. The concentration of that reactant makes no difference at all. If it's curved, well, you don't know. It could be first order, it could be second order. So plot the natural log of the concentration versus time. If that is linear for the natural log, then it's a first order reaction, meaning a proportional effect. If it's still curved, it's probably going to be second order. So now you should plot the 1 over the concentration versus time. And if you do get a straight line, then it is a second order reaction. So here we are describing these three types of plots. What do you think? There it is. There is a zeroth order reaction. It's simply concentration versus time is linear. Here's the first order. The natural log of the concentration versus time is the concentration versus time was curved. And if you see a steep curve, that's more likely for concentration versus time to be second order. But I wouldn't hang my hat on that. I would do the actual measurement instead. Take the slope of the line to get the rate constant for zeroth order. Take the slope of the line of natural log versus time to get the rate constant for a first order. Take the slope of 1 over the concentration versus time to get the rate constant for a second order reaction. You also do this just to verify that it is a first order and second order reaction. And that's how we do that. Now here's an actual question where they say the gas phase decomposition of nitrogen dioxide, blah, 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 was studied at a fixed temperature. They need to mention that because it'll change with temperature. And the following data was collected. Determine the order of the reaction with respect to NO2. Well, we have the plain old concentration of NO2. We have the log. The natural log works fine too. And we have 1 over the concentration. So whichever one of these is linear is going to tell you whether it's 0th, first, or second order. What I like to do is find somewhere where it doubles, say 5 to 10, and see if the rate goes down by a factor of 2. So from 0.017, does it go to half that? Here's 10. No, it's not linear. That's not half of that, right? If we double that, it's too high. Natural log 1.77 for 5. 10 is 2. No, that's not linear. But look at this. 58 doubled is about that. Let's double check it with 4 times. 5 to 20. 58 quadrupled does seem like it's going to be about 212. So this looks fairly linear right here. I would say this is a second order reaction. The best answer is to plot it, but who's going to do that, especially on a test? Maybe you would and make up your own plot. Yuck. But if you see it being in a linear fashion or close to, then that's the answer. So what they say is notice that the rate's doubling when your concentration is over time. And if you plot things, here is the log of the concentration versus time, still linear. Here's 1 over the concentration versus time. Aha, it's definitely linear. This one was curved. Therefore, the reaction is second order with respect to nitrogen dioxide. The slope of this line has been determined either mathematically or by hand, and it is about 10. And so that's how we determine the rate order and the rate constant.